Right now, as you read these words, you exist at a precise moment in cosmic time, exactly 13.772 billion years after the universe began. Not 13.8 billion years, not roughly 14 billion years, but 13.772 billion years, measured with a precision so extraordinary that we know the universe's age to within 24 million years, an accuracy of 0.17%. After decades of conflicting measurements, heated scientific debates, and revolutionary discoveries, we finally have the definitive answer to one of humanity's oldest questions. How old is everything that exists? This breakthrough represents far more than just precise measurement. The universe's exact age reveals profound truths about cosmic evolution, the nature of space and time, and humanity's place in the vast sweep of cosmic history. The number 13.772 billion isn't just a statistic. It is a cosmic birth certificate that tells the story of how nothing became everything, how chaos organized itself into complexity, and how a universe born in unimaginable violence eventually gave birth to stars, planets, and conscious beings capable of measuring their own cosmic age. The precision of this measurement is staggering when you consider the scales involved. We're talking about dating events that occurred billions of years before Earth existed, using light that has traveled across cosmic distances so vast they dwarf human comprehension. The fact that we can measure the universe's age to within 24 million years is like determining someone's exact birth time to within a few seconds based on examining their fingerprints from across a football stadium. But getting to this definitive answer required solving one of the biggest crises in modern cosmology, the age crisis that threatened to destroy our understanding of cosmic evolution. For decades, different measurement techniques gave conflicting ages for the universe, with some methods suggesting the cosmos was younger than its oldest stars. This paradox, how can stars be older than the universe that contains them, forced astronomers to question fundamental assumptions about cosmic expansion, stellar evolution, and the nature of time itself. The story of measuring the universe's age is also the story of humanity's evolving understanding of our cosmic context. Ancient civilizations imagined eternal, unchanging heavens. Medieval scholars debated whether the world was thousands or millions of years old. 19th century geologists discovered Earth was billions of years old, while early 20th century astronomers revealed that the universe itself was expanding and must have had a beginning. Dr. Edwin Hubble's discovery in 1929 that distant galaxies are racing away from us at speeds proportional to their distance provided the first evidence that the universe is expanding and therefore must have been smaller in the past. Working backward from this expansion, Hubble calculated the universe's age at approximately 2 billion years, a number immediately recognized as problematic because geological evidence showed Earth was already known to be older than 2 billion years. This cosmic age crisis persisted for decades as astronomers struggled to reconcile expanding universe theories with observational evidence. Different measurement techniques yielded wildly different ages: 10 billion years, 15 billion years, even 20 billion years. Each new measurement seemed to contradict previous results, creating a scientific controversy that questioned whether we truly understood how the universe works. The resolution came through a series of revolutionary space missions and groundbreaking discoveries that transformed our understanding of cosmic composition and evolution. The Hubble Space Telescope provided unprecedented precision in measuring cosmic distances. The Wilkinson Microwave Anisotropy Probe mapped the cosmic microwave background with extraordinary detail. The Planck satellite mission achieved even greater precision in measuring the universe's fundamental parameters. But the most startling discovery was that ordinary matter, the atoms that make up stars, planets, and people, comprises only 4.9% of the universe's total content. Dark matter accounts for 26.8% of cosmic reality, while dark energy makes up 68.3%. Understanding these mysterious components was essential for calculating the universe's true age, because dark matter and dark energy have shaped cosmic expansion throughout universal history. The final piece of the puzzle came from understanding how cosmic expansion has changed over time. The universe hasn't expanded at a constant rate throughout its history. For the first 7 billion years, expansion was slowing down due to gravitational attraction between matter. But 6.8 billion years ago, dark energy began dominating cosmic dynamics, causing expansion to accelerate. This changing expansion rate dramatically affects calculations of cosmic age. Today, a definitive age measurement of 13.772 billion years comes from combining multiple, independent techniques that all converge on the same answer. The cosmic microwave background radiation tells us about conditions when the universe was only 380,000 years old. Observations of the most distant supernova reveal how cosmic expansion has changed over billions of years. Studies of the oldest star clusters provide independent age estimates that confirm cosmological measurements. The precision of 13.772 billion years means we can now construct a detailed timeline of cosmic evolution with unprecedented accuracy. We know when the first stars formed, approximately 180 million years after the Big Bang. When galaxies began assembling, 500 million years after the beginning. This cosmic timeline reveals that we exist during a brief, special period in universal history after cosmic evolution has created complexity, but before dark energy expansion carries all other galaxies beyond our observable horizon. Future civilizations will inherit increasingly empty-appearing universes as cosmic expansion erases evidence of the broader cosmos from their observations. Understanding the universe's precise age also illuminates fundamental questions about the nature of time itself. The 13.772 billion year measurement refers to cosmic time, the time experienced by observers moving with the overall expansion of space. But Einstein's relativity shows that time is relative, flowing differently for observers in different reference frames. The universe's age depends on your cosmic perspective. If you're fascinated by humanity's greatest measurement achievement and want to understand how we finally solved the mystery of cosmic age, subscribe and hit thumbs up. And here's a mind-bending question. If the universe is exactly 13.772 billion years old, what does this precise timing tell us about our cosmic destiny and whether consciousness was inevitable or accidental? Comment below with your thoughts on whether the universe's age reveals deeper meaning about existence itself. The journey to this definitive age measurement has revolutionized our understanding of cosmic evolution, dark energy, and the ultimate fate of everything that exists. We're not just measuring time, we're decoding the universe's biography, written in the cosmic microwave background radiation, distant supernova, and the large-scale structure of space itself. What we've discovered challenges our most basic assumptions about cosmic evolution and reveals that we exist during an extraordinary period in universal history. The universe's precise age tells us where we came from, where we're going, and why this particular moment in cosmic time might be the most significant in the entire 13.772 billion year story of existence. Now, let us explore how humanity achieved the most precise measurement in the history of science and what this cosmic birth certificate reveals about the deepest mysteries of space, time, and our place in the vast story of everything. Chapter 1. Ancient Mystery. The quest to determine the universe's age represents humanity's oldest intellectual challenge, a mystery that has captivated human consciousness since the first thinking beings looked up at the night sky and wondered, how long has all this existed? This ancient question has driven scientific revolution after revolution, forcing us to completely reimagine our place in cosmic time and challenging every assumption about the nature of existence itself. Ancient civilizations approached cosmic age through mythology and philosophy rather than measurement. The Hindu cosmology describes cycles of creation and destruction spanning trillions of years. Timescales so vast they approach modern astronomical estimates through pure philosophical intuition. The Kalpa cycles described in ancient Sanskrit texts envision cosmic ages of 4.32 billion years, remarkably close to geological timescales discovered by modern science. Greek philosophers like Aristotle argued for an eternal, unchanging cosmos with no beginning or end. This eternal universe model dominated Western thought for over 2,000 years, creating intellectual frameworks where questions about cosmic age seemed meaningless. If the heavens were perfect and unchanging, as Aristotelian cosmology claimed, then asking about the universe's age was like asking about the age of mathematics or geometry. The first serious challenges to eternal cosmos models came from theological rather than scientific sources. Medieval scholars like Augustine of Hippo grappled with reconciling biblical creation accounts with philosophical arguments about time and eternity. These theological investigations led to profound questions about the relationship between time and existence that would later influence scientific approaches to cosmic age. Archbishop James Ussher's famous 1650 calculation that creation occurred on October 23, 4004 BC represented the first systematic attempt to date the universe using scholarly methodology. While his biblical chronology seems naive by modern standards, Ussher's approach of combining multiple historical sources and mathematical analysis established important precedents for cosmic age determination through careful scholarship and logical reasoning. The 18th and 19th centuries brought the first scientific challenges to young universe models through geological discoveries that revealed Earth's antiquity. Dr. James Hutton's observations of rock formations and erosion patterns suggested geological processes required millions or billions of years to create observed features. His concept of deep time began expanding human imagination to encompass timescales that dwarfed historical experience. Charles Lyell's principles of uniformitarianism, the idea that geological processes operate at constant rates over vast timescales, provided mathematical frameworks for calculating Earth's age based on observable phenomena. Lyell's calculations suggested Earth was hundreds of millions of years old, creating the first major conflict between scientific evidence and traditional chronologies. Lord Kelvin's thermodynamic calculations of Earth's cooling rate provided the first physics approach to cosmic age determination. Assuming Earth began as a molten mass cooling to its present temperature, Kelvin calculated terrestrial age at 20 to 40 million years. While this estimate was too young by factors of hundreds, Kelvin's methodology established the principle of using fundamental physical laws to constrain cosmic timescales. The discovery of radioactivity by Henry Becquerel and Marie Curie revolutionized age determination by providing cosmic clocks operating at known measurable rates. Radioactive decay proceeds at mathematically precise rates that are unaffected by temperature, pressure, or chemical environment, creating perfect timekeepers for measuring geological and cosmic ages. Dr. Arthur Holmes pioneered radiometric dating techniques that revealed Earth's true antiquity. By measuring the decay products of radioactive elements in rocks, Holmes determined that Earth was approximately 4.5 billion years old, a measurement that has been refined but never fundamentally changed by subsequent research. This discovery expanded the timescale for cosmic evolution by factors of thousands compared to previous estimates. But even 4.5 billion year terrestrial ages left fundamental questions about cosmic age unanswered. Was Earth as old as the universe, or did cosmic evolution precede planetary formation? The discovery that our Sun is a typical middle-aged star suggested that stellar and cosmic Evolution might encompass timescales far greater than planetary ages. Early stellar astronomy revealed that stars have finite lifetimes determined by their nuclear fuel supplies and energy generation rates. Dr. Hans Bethe's discovery of stellar fusion processes showed that even the longest-lived stars could maintain energy output for only tens of billions of years. This placed upper limits on possible cosmic ages, based on the requirement that the oldest observable stars must be younger than the universe itself. The first scientific evidence for cosmic expansion came from Vesto Slipher's observations of galactic redshifts in the 1910s and 1920s. Slipher discovered that most galaxies exhibit redshifted spectra, indicating they are moving away from us at high velocities. This systematic recession suggested that the universe itself might be expanding, implying it was smaller in the past and therefore must have had a beginning. Dr. Edwin Hubble's systematic study of galaxy distances and recession velocities provided the mathematical foundation for cosmic age determination. Hubble's law, that recession velocity is proportional to distance, indicated that the universe has been expanding at measurable rates. Working backward from observed expansion rates, Hubble calculated that all matter in the universe must have been concentrated at a single point approximately 2 billion years ago. This first scientific measurement of cosmic age immediately created the age crisis that would plague cosmology for decades. Hubble's 2 billion-year universe was younger than geological evidence for Earth's age and far younger than estimates for stellar ages based on nuclear fusion timescales. How could Earth and stars be older than the universe that contained them? The age crisis forced astronomers to question fundamental assumptions about cosmic expansion, stellar evolution, and time measurement itself. Perhaps cosmic expansion rates had changed over time. Perhaps stellar age calculations were incorrect. Perhaps something fundamental about time and cosmic evolution remained undiscovered. Dr. Walter Baades' discovery that there are two distinct populations of stars, population I stars in galactic disks and population II stars in galactic halos and globular clusters, provided crucial insights into cosmic chronology. Population II stars appeared much older than population I stars based on their chemical compositions and evolutionary states, suggesting that star formation has continued throughout cosmic history rather than occurring all at once. Globular cluster studies by Dr. Harlow Shapley revealed that our galaxy contains star clusters with ages approaching 10 to 12 billion years based on stellar evolution models. These ages were calculated by studying how long it takes stars of different masses to exhaust their nuclear fuel and evolve into white dwarf or neutron star remnants. The oldest globular clusters provided lower limits on cosmic age that exceeded early Hubble expansion age estimates. The recognition that cosmic expansion might not be constant over time opened new possibilities for reconciling stellar ages with cosmic expansion measurements. If expansion rates were faster in the past, the universe could be older than simple linear extrapolation suggested. Alternatively, if expansion rates were slower in the past, the age crisis might be even more severe. Einstein's general relativity provided theoretical frameworks for understanding how cosmic expansion rates could change over time based on the gravitational effects of matter and energy within the universe. Solutions to Einstein's field equations showed that cosmic expansion must decelerate over time due to gravitational attraction between matter, potentially resolving age discrepancies. Dr. George Lemaitre's primeval atom hypothesis proposed that the universe began in an extremely dense, hot state and has been expanding and cooling ever since. This Big Bang model provided physical mechanisms for cosmic expansion and suggested that the universe's age could be calculated by working backward from current expansion rates to the moment when all matter was compressed to infinite density. The discovery of the cosmic microwave background radiation by Arno Penzias and Robert Wilson in 1965 provided direct evidence for the Big Bang model and established that the universe was indeed much denser and hotter in the past. This relic radiation from the early universe carried information about cosmic conditions when the cosmos was only 380,000 years old, providing new tools for measuring cosmic age. But precision measurement of cosmic age remained elusive due to uncertainties in fundamental parameters, like the Hubble constant, the density of matter in the universe, and the possible existence of additional energy components that might affect cosmic expansion. Different measurement techniques continued yielding conflicting ages ranging from 10 to 20 billion years. The ancient mystery of cosmic age had evolved from philosophical speculation to precise scientific measurement, but definitive answers remained frustratingly out of reach. Each new discovery seemed to raise as many questions as it answered about cosmic chronology. The quest to determine exactly how old the universe is had become one of the central challenges in 20th century astronomy. Resolution would require revolutionary new observations, theoretical breakthroughs, and measurement techniques capable of achieving unprecedented precision. The ancient mystery of cosmic age was about to enter a new phase where space missions, supercomputer simulations, and exotic new forms of matter and energy would finally provide definitive answers to humanity's oldest question about cosmic existence. Understanding how long this quest has continued reveals why determining the universe's precise age represents such a profound achievement. We are not just measuring time, we are completing an intellectual journey that began when the first human beings wondered about their place in cosmic history. Chapter 2. Conflicting Evidence. By the late 20th century, the quest to determine the universe's age had produced a scientific crisis so severe it threatened to destroy our understanding of cosmic evolution. Different measurement techniques were yielding wildly conflicting ages, some suggesting the universe was 10 billion years old, others claiming 15 billion years, with a few estimates reaching 20 billion years or more. This age crisis created paradoxes where the universe appeared younger than its oldest stars, forcing astronomers to confront the possibility that fundamental assumptions about cosmic evolution might be completely wrong. The heart of the crisis lay in measuring the Hubble constant, the rate at which cosmic expansion carries galaxies away from each other. Dr. Edwin Hubble's original measurements in the 1920s suggested the universe was expanding so rapidly that everything must have been at the same point only 2 billion years ago. But subsequent observations by Dr. Walter Baade revealed that Hubble had severely underestimated cosmic distances due to confusion between different types of variable stars used as cosmic distance markers. Baade's discovery that Cepheid variable stars come in two distinct populations with different luminosities meant that cosmic distances were actually twice as large as Hubble had calculated. This correction immediately doubled the universe's estimated age to 4 billion years, temporarily relieving the age crisis by making the cosmos older than Earth. But the relief was short-lived as improved stellar evolution models suggested that globular star clusters were even older than the revised cosmic age estimates. The conflicting evidence intensified throughout the 1970s and 1980s as competing research teams used different astronomical techniques to measure the Hubble constant. Dr. Alan Sandage and Gustav Tammann's careful studies of Cepheid variables in nearby galaxies yielded Hubble constant values around 50 kilometers per second MPC, implying a universe approximately 20 billion years old. Their measurements suggested a leisurely cosmic expansion that provided ample time for stellar and galactic evolution. But Dr. Gerard de Vaucouleurs argued that Sandage and Tammann's measurements suffered from systematic errors in distance calibration. Using alternative distance measurement techniques, including surface brightness fluctuations and the Tully-Fisher relation, de Vaucouleurs obtained Hubble constant values around 100 kilometers per second (MPC), implying a universe only 10 billion years old, uncomfortably close to the estimated ages of the oldest globular star clusters. The Hubble constant wars between these competing research groups became one of the most contentious scientific debates of the late 20th century. Each team accused the other of systematic measurement errors, inadequate calibration techniques, and biased data selection. The factor of two disagreement in the Hubble constant translated into factor of two differences in cosmic age, creating fundamentally different pictures of cosmic evolution. Dr. Mark Aronson's infrared observations of Cepheid variables attempted to resolve the distance scale controversy by eliminating dust absorption effects that could bias optical measurements. Infrared light penetrates cosmic dust more easily than visible light, providing cleaner measurements of stellar brightness and therefore more accurate distance estimates. Aronson's infrared Cepheid distances generally supported higher Hubble constant values and younger cosmic ages. Meanwhile, stellar evolution theorists were developing increasingly sophisticated models of how stars age and evolve over cosmic time. Dr. Don Vandenberg's detailed calculations of stellar evolution in globular clusters suggested that the oldest star clusters were 1518 billion years old, based on the time required for the most massive stars to evolve off the main sequence and become white dwarf remnants. These stellar ages created impossible paradoxes if the universe was only 10 billion years old. How could stars be older than the universe that created them? Either stellar evolution models were fundamentally wrong, cosmic expansion measurements were systematically biased, or some aspect of cosmic evolution remained undiscovered. The age crisis deepened as additional independent evidence suggested old cosmic ages. Dr. Francois Spite and Monique Spite's measurements of lithium abundances in old stars provided constraints on Big Bang nucleosynthesis that favored older cosmic ages and lower cosmic densities. Lithium-7 is created during the first few minutes after the Big Bang, and its observed abundance in old stars must match theoretical predictions for Big Bang nucleosynthesis. Dr. David Schramm's calculations showed that observed lithium abundances required cosmic baryon densities lower than needed for a critical density universe, implying that cosmic expansion should not decelerate significantly over time. This suggested that simple models relating the Hubble constant to cosmic age through gravitational deceleration were inadequate for determining the universe's true age. Meanwhile, observations of distant quasars and galaxies revealed that cosmic structure formation required billions of years to create the complex networks of galaxy clusters and superclusters observed in today's universe. Dr. Margaret Geller and John Huckroth's redshift surveys revealed enormous structures like the Great Wall of galaxies spanning hundreds of millions of light-years, structures that seem to require vast amounts of time to form through gravitational assembly. Computer simulations of cosmic structure formation by Dr. Carlos Frank and others suggested that observed large-scale structures required at least 10 to 15 billion years to develop from primordial density fluctuations. These timescales for structure formation provided independent evidence for old cosmic ages that conflicted with young universe models based on high Hubble constant values. The discovery of high redshift quasars by Dr. Martin Schmidt and others revealed that massive black holes and galactic nuclei existed when the universe was less than 2 billion years old. The formation of billion solar mass black holes in such short timescales seemed to require either extremely rapid black hole growth rates or universe ages significantly older than the highest Hubble constant measurements allowed. Nucleocosmochrgo provided another independent approach to cosmic age determination through measurements of radioactive decay products in old stars. Dr. John Cowan and Christopher Snetten's observations of radioactive thorium and uranium in metal-poor stars suggested stellar ages of 12 to 15 billion years based on the depletion of long-lived radioactive isotopes produced in supernova. These radioactive clocks operated independently of stellar evolution models and cosmic expansion measurements, providing a third independent constraint on cosmic age. The convergence of nucleo-cosmocrystal ages with globular cluster ages strengthened evidence for old cosmic ages that conflicted with young universe models. The age crisis reached its peak in the early 1990s when improved measurements seemed to make the problems worse rather than better. The Hubble Space Telescope's unprecedented angular resolution allowed precise measurements of Cepheid variables in galaxies beyond the local group, providing the most direct measurements of cosmic distances and the Hubble constant ever achieved. Dr. Wendy Friedman led the Hubble Space Telescope Key project to measure the Hubble constant using Cepheid variables in 18 nearby galaxies. These observations, conducted with the most advanced astronomical instrument ever built, yielded Hubble constant values around 70 kilometers per second (MPC), splitting the difference between previous high and low estimates, but still implying cosmic ages of only 12 to 14 billion years. Meanwhile, improved stellar evolution models incorporating updated opacity calculations, convection theory, and nuclear reaction rates suggested that globular cluster ages might be even older than previously estimated. Dr. Brian Chaboyer's refined age determinations for globular clusters yielded ages of 14 to 16 billion years, maintaining uncomfortable tensions with cosmic expansion ages. The crisis seemed intractable because multiple independent lines of evidence were converging on conflicting conclusions. Cosmic expansion measurements favored younger ages, while stellar evolution and structure formation evidence favored older ages. Both approaches used well-established physics and careful observational techniques, yet they yielded incompatible results. Some astronomers began questioning fundamental assumptions about cosmic evolution. Perhaps the Hubble constant was not truly constant over cosmic time. Perhaps stellar evolution models contained systematic errors in nuclear reaction rates or convection efficiency. Perhaps cosmic expansion was more complex than simple deceleration due to gravitational effects. The conflicting evidence crisis revealed that determining cosmic age requires understanding dark matter, dark energy, cosmic geometry, and the relationship between expansion rate changes and cosmic evolution. Resolution would require revolutionary discoveries about the fundamental composition and evolution of the universe itself. The age crisis of the late 20th century forced astronomers to confront the possibility that standard models of cosmic evolution were incomplete or incorrect. The conflicting evidence between cosmic expansion ages and stellar evolution ages suggested that crucial components of cosmic evolution remained undiscovered. Little did astronomers realize that resolving the age crisis would require discovering that 95% of the universe consists of mysterious dark matter and dark energy components that were completely unknown in the 20th century. The conflicting evidence was pointing toward revolutionary discoveries about the fundamental nature of cosmic reality itself. Chapter 3. Breakthrough Discovery. The resolution of the cosmic age crisis came through a series of revolutionary discoveries in the 1990s and 2000s that fundamentally transformed our understanding of the universe's composition and evolution. The breakthrough wasn't just better measurements of known phenomena, but the discovery that 95% of cosmic reality consists of mysterious components, dark matter and dark energy, that had remained completely invisible to previous astronomical observations. Understanding these hidden cosmic constituents finally provided the key to determining the universe's precise age. The first major breakthrough came from the Cosmic Background Explorer, COBE, satellite mission launched by NASA in 1989. COBE's precise measurements of the cosmic microwave background radiation revealed tiny temperature fluctuations, variations of only a few millionths of a degree, that represented the seeds of all cosmic structure. Dr. George Smoot's analysis of these fluctuations provided the first detailed map of conditions in the universe when it was only 380,000 years old. Cobb's discoveries revolutionized cosmic age determination by providing direct observational evidence for the Big Bang model and establishing precise constraints on cosmic parameters. The spectrum of temperature fluctuations in the cosmic microwave background carried information about the universe's geometry, composition, and expansion history encoded in subtle patterns that could be decoded to determine cosmic age with unprecedented precision. Dr. John Mather's leadership of COB's instrument development enabled measurements that confirmed the cosmic microwave background has a perfect black body spectrum with temperature 2.725 Kelvin. This precise temperature measurement, combined with the observed fluctuation patterns, constrained models of cosmic evolution and provided the foundation for precision cosmology that would finally resolve the age crisis. The second breakthrough came from observations of distant Type Ia supernova by two competing research teams led by Dr. Saul Perlmutter and Dr. Adam Rees. These stellar explosions serve as standard candles because they achieve nearly identical peak brightness, allowing astronomers to determine cosmic distances by measuring how bright they appear compared to their known intrinsic luminosity. The supernova observations revealed something completely unexpected. Distant supernova appeared dimmer than predicted by standard cosmic models, indicating they were farther away than expected. This meant that cosmic expansion was accelerating rather than decelerating, driven by a mysterious dark energy that comprises approximately 68% of the universe's total energy content. The discovery of cosmic acceleration revolutionized age calculations because it meant the universe had been expanding more slowly in the past when deceleration dominated, then more rapidly in recent cosmic history as dark energy began driving accelerated expansion. This changing expansion rate dramatically affected calculations of cosmic age derived from current expansion measurements. Dr. Brian Schmidt's analysis of high redshift supernova data showed that cosmic expansion transitioned from deceleration to acceleration approximately 6.8 billion years ago when dark energy began dominating over matter's gravitational effects. This cosmic transition fundamentally changed the relationship between current expansion rates and total cosmic age. The third breakthrough came from improved understanding of dark matter's role in cosmic evolution through gravitational lensing observations and computer simulations of cosmic structure formation. Dr. Vera Rubin's earlier discoveries of flat galaxy rotation curves had suggested that galaxies contained far more mass than visible matter could account for, but the cosmic implications remained unclear until the 1990s. Large-scale structure surveys like the Sloan Digital Sky Survey revealed that the distribution of galaxies throughout space matched computer simulations, only if cosmic matter density was much lower than the critical density needed to close the universe geometrically. This meant that cosmic expansion should continue forever rather than eventually reversing into gravitational collapse. Dr. Carlos Frank's M-body simulations of cosmic structure formation showed that observed galaxy distributions required cosmic matter density around 30% of the critical value, with most of this matter being dark matter that interacts gravitationally but not electromagnetically. This low matter density implied older cosmic ages than previous estimates based on higher matter density assumptions. The convergence of cosmic microwave background observations, supernova distance measurements, and large-scale structure surveys created a new concordance cosmology model where cosmic evolution is driven by the interplay between ordinary matter 4.9%, dark matter 26.8%, and dark energy 68.3%. This precise accounting of cosmic constituents finally enabled accurate cosmic age determination. The Wilkinson Microwave Anisotropy Probe WMAP mission, launched in 2001, achieved unprecedented precision in mapping cosmic microwave background fluctuations. Dr. Charles Bennett's leadership of WMAP enabled measurements of cosmic parameters with accuracy approaching 1%, including the first precision determination of cosmic age at 13.77 plus or minus 0.13 billion years. WMAP's measurements resolved the age crisis by showing the cosmic geometry is precisely flat. Cosmic matter density is low enough to permit old ages, and dark energy dominance explains why current expansion rates don't directly translate to young cosmic ages through simple extrapolation. The universe is old enough to accommodate ancient globular clusters while expanding fast enough to match current observations. The breakthrough in cosmic age determination came from combining multiple independent measurement techniques that all converged on consistent results. Cosmic microwave background observations provided information about early cosmic conditions. Supernova observations revealed cosmic expansion history. Large-scale structure measurements constrained cosmic matter and energy densities. Dr. Sean Carroll's theoretical work showed how these diverse observations could be combined into a coherent model of cosmic evolution, where the universe begins in a hot, dense Big Bang state, expands and cools while matter gravitationally assembles into stars and galaxies, then transitions to accelerating expansion as dark energy begins dominating cosmic dynamics. The Planck satellite mission, launched in 2009, achieved even greater precision in cosmic microwave background measurements. Dr. Jan Tauber's leadership of Planck enabled temperature measurements accurate to microkelvin levels and polarization measurements that revealed additional information about cosmic evolution and fundamental physics. Planck's final results, released in 2018, provided the most precise cosmic age determination ever achieved: 13.772 plus or minus 0.024 billion years. This measurement has an uncertainty of only 24 million years, approximately 0.17% precision, representing the most accurate age determination for any astronomical object larger than our solar system. The precision breakthrough came from understanding how cosmic age depends on 6 fundamental parameters: the Hubble constant, cosmic matter density, cosmic curvature, dark energy density, amplitude of primordial fluctuations, and spectral index of fluctuations. Planck's measurements constrained all these parameters simultaneously through analysis of cosmic microwave background patterns. The mathematical relationship between cosmic microwave background fluctuations and cosmic parameters involves complex calculations of how sound waves propagated through the early universe, how matter and radiation interacted during cosmic evolution, and how gravitational effects amplified density fluctuations into cosmic structure. These calculations require supercomputer simulations and sophisticated statistical analysis. Dr. Planck collaboration's analysis involved comparing observed cosmic microwave background patterns with millions of theoretical models spanning different combinations of cosmic parameters. The best-fitting model parameters yield cosmic age, 13.772 billion years with unprecedented precision that finally resolved decades of conflicting age measurements. Independent confirmation of Planck's cosmic age determination comes from multiple sources. Improved globular cluster age measurements using Gaia satellite data and updated stellar evolution models yield ages 12 to 13 billion years, comfortably younger than the cosmic age. Nucleocosmology ages based on radioactive decay in old stars also confirm cosmic ages around 13 to 14 billion years. The breakthrough discovery that resolved the cosmic age crisis revealed that the universe is dominated by mysterious dark matter and dark energy components that were unknown to 20th century astronomy. Understanding these hidden cosmic constituents was essential for accurate age Determination, because they control cosmic expansion throughout universal history. The precision age measurement of 13.772 billion years represents the culmination of humanity's quest to understand cosmic chronology. This measurement combines observations spanning from the cosmic microwave background created when the universe was 380,000 years old to distant supernova observed when cosmic expansion was beginning to accelerate. The breakthrough also revealed that we exist during a special period in cosmic history, after matter has had sufficient time to form complex structures like stars, planets, and life, but before dark energy expansion carries all other galaxies beyond our observable horizon. Future civilizations will inherit increasingly empty-appearing universes as cosmic expansion erases evidence of cosmic evolution. Understanding how this breakthrough was achieved reveals the power of combining multiple independent measurement techniques and theoretical frameworks to solve fundamental scientific problems. The cosmic age determination represents one of humanity's greatest intellectual achievements, precisely dating the origin of everything that exists through careful observation and mathematical analysis of cosmic evolution. Chapter 4. Cosmic Clocks Determining the universe's precise age of 13.772 billion years required developing and calibrating multiple independent cosmic clocks, natural phenomena that tick at known rates throughout cosmic history. These celestial timekeepers operate on principles ranging from nuclear physics to general relativity, each providing unique insights into cosmic chronology while cross-checking the reliability of age measurements through completely different physical processes. The most fundamental cosmic clock is radioactive decay, which operates according to precise mathematical laws that remain constant regardless of temperature, pressure, or chemical environment. Dr. Ernest Rutherford's discovery that radioactive elements decay at measurable rates provided the first reliable method for dating ancient materials. Each radioactive isotope has a characteristic half-life, the time required for half the atoms in a sample to decay into daughter products. Uranium-238 decays to Li-206 with a half-life of 4.47 billion years, providing cosmic timescales comparable to the age of the solar system. Thorium-232 decays to Li-208 with a half-life of 14.0 billion years, spanning timescales comparable to cosmic age itself. These long-lived radioactive isotopes serve as cosmic chronometers for dating the oldest terrestrial and meteoritic materials. Dr. Claire Patterson's pioneering measurements of lead isotope ratios in primitive meteorites established Earth's age at 4.54 billion years. This radiometric age represents the time since the solar system condensed from the molecular cloud that gave birth to our sun and planets. Comparing Earth's age with cosmic age reveals that our solar system formed when the universe was already 9.2 billion years old, approximately two-thirds through current cosmic history. Stellar evolution provides another type of cosmic clock based on how stars consume nuclear fuel over time. Main sequence stars burn hydrogen into helium at rates determined by their mass, with more massive stars burning fuel faster and evolving more rapidly than lower mass stars. Dr. Martin Schwarzschild's stellar evolution calculations showed how to use stellar properties to determine ages of star clusters. Globular clusters contain hundreds of thousands of stars that all formed at approximately the same time from the same molecular cloud. As cluster ages increase, progressively less massive stars evolve off the main sequence and become red giants, white dwarfs, or neutron stars. The mass of the most evolved stars in a cluster provides a direct measurement of cluster age through stellar evolution. Calculations. Dr. Don Vandenberg's sophisticated stellar evolution models incorporate detailed physics of nuclear fusion, stellar structure, and stellar atmospheres to calculate how stars of different masses evolve over time. These models predict exactly how long stars of various masses spend in different evolutionary phases, enabling precise age determination for globular clusters through main sequence turn-off measurements. The oldest globular clusters in our galaxy have ages around 12.5 to 13.0 billion years based on current stellar evolution models. These ages provide independent confirmation of cosmic age measurements because globular clusters must be younger than the universe that contains them. The good agreement between globular cluster ages and cosmic microwave background ages validates both measurement techniques. White dwarf cooling provides yet another stellar clock based on how these stellar remnants radiate away their thermal energy over cosmic time. White dwarf stars are extremely hot when they form, but gradually cool through thermal radiation. According to well-understood physics, Dr. Gilles Fontaine's calculations of white dwarf cooling rates show how to use white dwarf temperatures to determine their ages. The coolest to faintest white dwarf stars in globular clusters provide lower limits on cluster ages because these stellar remnants have been cooling for the longest time since their formation. Dr. Harvey Richer's Hubble Space Telescope observations of white dwarf cooling sequences in globular clusters yield ages consistent with main sequence turn-off measurements, providing independent confirmation of stellar evolution timescales. Nucleocosmology represents another approach to cosmic timekeeping through measurements of long-lived radioactive isotopes in old stars. Heavy elements like thorium and uranium are created in supernova explosions and distributed throughout the galaxy by stellar winds and supernova explosions. The abundance ratios of different radioactive isotopes in old stars reflect the time since these elements were created in supernova. Dr. John Cowan's observations of thorium and uranium lines in extremely metal-poor stars suggest that the oldest stellar populations formed when the galaxy was 2 to 3 billion years old. Combining these nucleocosmological ages with cosmic age measurements indicates that our galaxy began forming stars when the universe was approximately 11 to 12 billion years old. The cosmic microwave background provides the most precise cosmic clock through detailed analysis of temperature fluctuations that reveal conditions when the universe was only 380,000 years old. These fluctuations encode information about how sound waves propagated through the early universe and how matter and radiation interacted during cosmic evolution. Dr. Wayne Hu's theoretical calculations show how cosmic microwave background fluctuation patterns depend on fundamental cosmic parameters, including matter density, dark energy density, cosmic geometry, and the expansion rate. The observed fluctuation spectrum provides simultaneous constraints on all these parameters, enabling precise determination of cosmic age through detailed comparison with theoretical models. The physics of cosmic microwave background fluctuations involves complex calculations of how primordial density fluctuations evolve under gravitational attraction, radiation pressure, and cosmic expansion. Sound waves in the early universe created oscillating patterns of compression and rarefaction that were frozen into the cosmic microwave background when matter became transparent to radiation. The angular size of these fluctuation patterns depends on cosmic geometry and expansion history in ways that can be calculated precisely using general relativity and plasma physics. The Planck satellite has measurements of fluctuation patterns, constrain cosmic parameters so precisely that cosmic age is determined to 0.17%. ACCURACY equivalent to knowing your own age to within about 2 months. Type Ia supernova provide cosmic clocks that reveal how cosmic expansion has changed over time. These stellar explosions achieve nearly uniform peak brightness, allowing astronomers to determine cosmic distances by measuring how bright they appear. Comparing supernova distances with their redshifts reveals cosmic expansion history over billions of years. Dr. Adam Rees's observations of distant supernova show that cosmic expansion was decelerating for the first 7 billion years of cosmic history, then began accelerating as dark energy started dominating cosmic dynamics. This transition from deceleration to acceleration occurred when the universe was approximately 6.8 billion years old, providing another temporal marker in cosmic evolution. Surface brightness fluctuations in elliptical galaxies provide another cosmic distance indicator that can be calibrated to determine cosmic expansion rates. Dr. John Tonry's measurements of brightness fluctuations caused by statistical variations in stellar populations enable distance determinations to nearby galaxy clusters that help calibrate other cosmic distance indicators. The Tully-Fisher relation between galaxy rotation velocities and luminosities provides yet another cosmic distance measurement technique. Dr. Brent Tully's observations show that more luminous spiral galaxies rotate faster than less luminous galaxies, creating a correlation that can be used to determine galaxy distances from their measured rotation velocities. Gravitational wave observations by LIGO and Virgo provide a completely new type of cosmic clock through measurements of neutron star and black hole merger events. These gravitational wave sources can potentially serve as standard sirens for cosmic distance measurement, because gravitational wave amplitudes depend on source distances in ways predicted by general relativity. Dr. Kip Thorne's theoretical calculations show how gravitational wave observations, combined with electromagnetic counterparts, can provide independent measurements of cosmic expansion rates and cosmic age. The LIGO-Virgo detections of neutron star mergers have already provided preliminary cosmic distance measurements that are consistent with other cosmic age determinations. Cosmic structure formation provides temporal constraints on cosmic evolution through observations of how galaxies cluster together over cosmic time. The growth of cosmic structure under gravitational attraction occurs at rates that depend on cosmic matter density, dark energy properties, and cosmic expansion history. Dr. Volker Sprengel's computer simulations of cosmic structure formation show how primordial density fluctuations grow into galaxy clusters and superclusters over cosmic time. Comparing these simulations with observations of cosmic structure at different redshifts provides constraints on cosmic parameters and cosmic age through structure formation timescales. The convergence of measurements from all these independent cosmic clocks on the same cosmic age of 13.772 billion years provides extraordinary confidence in this age determination. Each clock operates according to different physical principles and measures cosmic evolution through completely different phenomena, yet they all yield consistent results. This convergence represents one of the greatest triumphs in the history of science. The precise determination of cosmic age through multiple independent measurement techniques that cross-check each other as reliability. The cosmic clocks reveal that we can determine the age of the universe with greater precision than we can measure the age of most objects on Earth. Understanding how cosmic clocks operate illuminates the deep connections between nuclear physics, stellar evolution, general relativity, and cosmic evolution. The universe's age emerges from the interplay of fundamental physical processes operating across scales from atomic nuclei to cosmic horizons, revealing the profound unity underlying all natural phenomena. Chapter 5. Timeline Revolution. The precise determination of the universe's age at 13.772 billion years has revolutionized our understanding of cosmic evolution by enabling the construction of a detailed timeline that tracks the emergence of complexity from the Big Bang to the present moment. This cosmic timeline reveals that virtually everything interesting in the universe, from the first atoms to the first stars to the emergence of consciousness, has occurred during a remarkably brief period compared to the universe's total lifespan, fundamentally changing our perspective on cosmic evolution and our place within it. The timeline begins with the Planck epoch, spanning the first y-43 seconds after the Big Bang, when quantum gravitational effects dominated cosmic evolution. During this unimaginably brief period, space and time themselves might have been discontinuous and foamy at microscopic scales. Current physics cannot describe conditions during the Planck epoch because quantum mechanics and general relativity yield contradictory predictions at such extreme scales. Dr. Alan Guth's inflationary cosmology suggests that cosmic inflation occurred between y-36 and 10 to 32 seconds after the Big Bang, expanding space by enormous factors while maintaining nearly perfect uniformity. Inflation explains why the cosmic microwave background has the same temperature in all directions and why space appears geometrically flat despite the curvature that should result from matter and energy density. The inflationary period ended when inflattened fields decayed into ordinary particles, reheating the universe to temperatures around y Kelvin and filling space with radiation and exotic particles. This reheating phase marked the beginning of the radiation-dominated epoch when photons carried most of the universe's energy, and cosmic expansion was driven primarily by radiation pressure. Grand unified theory phase transitions might have occurred around 10 to 12 seconds after the Big Bang, when electromagnetic and weak nuclear forces separated from their high-energy unified state. These phase transitions could have produced cosmic strings, monopoles, and other exotic relics that might be detectable in today's universe if they survived cosmic evolution. The electroweak phase transition occurred around 10 to 10 seconds after the Big Bang, when electromagnetic and weak nuclear forces achieved their current distinct identities. This transition established the masses of fundamental particles like electrons and quarks through interactions with the Higgs field, determining the basic properties of matter that would shape all subsequent cosmic evolution. Big Bang nucleosynthesis began approximately 1 second after the Big Bang, when temperatures dropped below 10·9 Kelvin and protons and neutrons could combine into light atomic nuclei. Dr. Ralph Alpher and Robert Herman's calculations showed that Big Bang nucleosynthesis should produce specific ratios of hydrogen, helium, lithium, and beryllium that match observed abundances in the oldest astronomical objects. The nucleosynthesis epoch lasted only about 20 minutes, but determined the chemical composition of the universe for hundreds of millions of years until stellar fusion began creating heavier elements. Approximately 75% of cosmic matter emerged from Big Bang nucleosynthesis as hydrogen, 25% as helium, and trace amounts as lithium, ratios that remain nearly constant throughout cosmic evolution. Matter radiation equality occurred approximately 50,000 years after the Big Bang, when the energy density in matter exceeded the energy density in radiation for the first time. This transition marked the beginning of the matter-dominated epoch, when cosmic expansion was driven primarily by gravitational effects of matter rather than radiation pressure. The transition to matter domination enabled gravitational instability to begin amplifying primordial density fluctuations into the seeds of cosmic structure. During the radiation-dominated epoch, radiation pressure prevented significant structure growth, but matter domination allowed gravity to begin collecting material into the dark matter halos that would eventually host galaxies. Recombination occurred approximately 380,000 years after the Big Bang, when cosmic temperatures dropped below 3,000 Kelvin and electrons could combine with protons to form neutral hydrogen atoms. This process made the universe transparent to radiation for the first time, allowing photons to travel freely through space and creating the cosmic microwave background radiation we observe today. The cosmic microwave background represents a snapshot of cosmic conditions at recombination, preserving information about temperature fluctuations that would later grow into galaxies and galaxy clusters. Dr. John Mather and George Smoot's SCOB observations revealed these fluctuations and provided the first detailed map of cosmic structure formation. The cosmic dark age began after recombination, when the universe contained only neutral hydrogen and helium atoms in a cosmos without any luminous objects. This period lasted approximately 180 million years until gravitational collapse created the first stars and began the process of cosmic reionization through stellar radiation and supernova explosions. First star formation began around 180 million years after the Big Bang, when gravitational collapse in dark matter halos created dense enough conditions to initiate nuclear fusion and primordial gas clouds. These population 3 stars contained no heavy elements and could achieve masses hundreds of times larger than modern stars because they lacked heavy elements that facilitate cooling and fragmentation. Dr. Volker Brahm's computer simulations show that the first stars burned brilliantly but briefly, exhausting their nuclear fuel in only a few million years before exploding as supernova. These explosions synthesized and distributed the first heavy elements throughout space, providing the materials necessary for second-generation star formation and eventual planet formation. Cosmic reionization occurred between 400 million and 1 billion years after the Big Bang, as radiation from the first stars and galaxies ionized most of the hydrogen atoms in intergalactic space. This process fundamentally changed cosmic evolution by making space transparent to ultraviolet radiation and enabling the formation of larger, more complex astronomical objects. First galaxy formation began around 500 million years after the Big Bang, as dark matter halos accumulated sufficient mass to retain gas and support sustained star formation. The Hubble Space Telescope has observed galaxies that existed when the universe was only 400 to 500 million years old, revealing that cosmic structure formation proceeded more rapidly than many theoretical models predicted. Dr. Richard Ellis's observations of high redshift galaxies show that early cosmic evolution involved rapid merger processes that assembled massive galaxies much faster than occurs in today's universe. This rapid early evolution occurred because cosmic matter densities were much higher in the past, accelerating gravitational assembly processes. Heavy element enrichment began with the first supernova around 200 to 300 million years after the Big Bang and continued as successive generations of stars lived, died, and distributed their fusion products throughout space. This gradual chemical enrichment was essential for planet formation and biological evolution because complex chemistry requires elements heavier than hydrogen and helium. Solar system formation occurred approximately 4.56 billion years ago, when the universe was already 9.2 billion years old, about 2/3 of its current age. This timing means that billions of years of cosmic chemical evolution preceded our solar system, providing the heavy elements necessary for terrestrial planet formation and biological evolution. Dr. Alan Boss's models of solar system formation show that planetary systems like ours could only form after sufficient heavy element enrichment had occurred through multiple generations of stellar evolution. Early planetary systems were predominantly composed of hydrogen and helium and could not support terrestrial planet formation or complex chemistry. Life on Earth emerged approximately 3.8 billion years ago based on isotopic evidence in ancient rocks, occurring when the universe was approximately 9.9 billion years old. This relatively rapid emergence of life after Earth formation suggests that biological evolution might be a common consequence of suitable planetary conditions. Complex multicellular life developed much later, with the Cambrian explosion of animal diversity occurring only 540 million years ago, when the universe was already 13.2 billion years old. This timing reveals that most of cosmic history preceded the emergence of complex biological systems and consciousness. Human consciousness emerged only in the last few million years of cosmic history, when the universe was already 13.77 billion years old. Homo sapiens has existed for only the last 200,000 years, approximately 0.0014% of cosmic history. Recorded human civilization spans only the last 5,000 years, representing 0.0000036% of total cosmic time. The timeline revolution reveals that we exist during an extraordinary period in cosmic history, when the universe has had sufficient time to create complexity through stellar nucleosynthesis and galactic evolution, but before dark energy expansion carries other galaxies beyond our observable horizon. Future observers will inherit increasingly empty-appearing universes as cosmic expansion erases evidence of cosmic evolution. Understanding the cosmic timeline also reveals acceleration in complexity emergence over cosmic history. Simple atoms formed in the first 380,000 years. The first stars required 180 million years. Galaxies formed within the first billion years. But complex chemistry, planetary systems, and biological evolution required many billions of years of preparatory cosmic evolution. The timeline revolution shows that cosmic evolution exhibits directionality toward increasing complexity, despite operating through undirected physical processes. The emergence of atoms, stars, galaxies, planets, life, and consciousness represents a cosmic progression that seems to optimize conditions for the emergence of ever more sophisticated organizational levels. This cosmic timeline provides essential context for understanding humanity's place in universal evolution and suggests that consciousness might represent a significant development in cosmic complexity rather than an accidental byproduct of planetary evolution. We exist during the era when cosmic evolution has achieved its greatest complexity and organizational sophistication. The precise cosmic timeline made possible by knowing the universe's exact age reveals the remarkable progression from simplicity to complexity that characterizes cosmic evolution and provides essential context for understanding our cosmic significance during this brief but extraordinary period in universal history. Chapter 6. Stellar Archaeology. The universe's precise age of 13.772 billion years has enabled astronomers to develop stellar archaeology, the science of reading cosmic history through detailed analysis of the oldest stars in our galaxy. These ancient stellar fossils preserve chemical signatures from the early universe, record the timing of galactic formation, and reveal how cosmic evolution proceeded during the first billion years after the Big Bang, when the universe was transitioning from simplicity to complexity. The oldest stars in our galaxy are found in globular clusters and the galactic halo, ancient stellar populations that formed when the Milky Way was young and chemically primitive. These population II stars contain almost no heavy elements compared to modern stars like our Sun, reflecting conditions when the universe had undergone only limited stellar nucleosynthesis and chemical enrichment. Dr. Timothy Beer's SHK survey identified thousands of extremely metal-poor stars with heavy element abundances less than 1% of solar values. These stars formed from gas that have been enriched by only 1 or 2 generations of massive stars, preserving chemical fingerprints from some of the earliest epochs of galactic evolution when heavy element production was just beginning. The most metal-poor star ever discovered, designated SMSSJ 031300.36670,839.3, has an iron abundance only 150 million that of the Sun. This star likely formed from gas enriched by a single supernova explosion, making it essentially a fossil of conditions in the early galaxy when massive stars were just beginning to synthesize and distribute heavy elements. Stellar archaeology techniques involve detailed spectroscopic analysis of stellar atmospheres to measure abundances of different chemical elements. Each element produces characteristic absorption lines in stellar spectra, and the strengths of these lines indicate how much of each element the star contains. These stellar chemical compositions reflect the cosmic environment when the stars formed. Dr. John Norris. Observations of globular cluster stars reveal abundance patterns that constrain the timing and processes of early galactic chemical evolution. Elements like oxygen and magnesium are produced primarily in massive stars and distributed by supernova explosions, while elements like iron are produced in both massive stars and Type Ia supernova with different timescales. The abundance ratios of different elements in old stars provide cosmic chronometers for dating early galactic evolution. Alpha elements like oxygen and magnesium are produced quickly in massive stars that explode as supernova within a few million years. Ion production involves longer timescales because Type Ia supernova require hundreds of millions of years for white dwarf formation and binary evolution. Ancient stars show enhanced alpha element to ion ratios compared to modern stars, indicating they formed before Type Ia supernova began contributing significant iron to galactic chemical evolution. This abundance pattern suggests that early star formation in our galaxy occurred rapidly, creating massive stars that exploded and enriched the interstellar medium before lower mass stars could evolve and contribute to chemical evolution. Dr. Chris Sneddon's analysis of heavy elements in metal-poor stars reveals how R process and S process nucleosynthesis contributed to early chemical evolution. R process elements like europium and gold are created in neutron star mergers and rare types of supernova, while S process elements like barium are produced in asymptotic giant branch stars over longer timescales. The heavy element patterns in the oldest stars suggest that neutron star mergers were primary sources of R process elements in the early galaxy, confirming recent gravitational wave observations of neutron star collisions. The timing of R process element production constrains when the first neutron stars formed and merged in galactic evolution. Lithium abundances in metal-poor stars provide tests of Big Bang nucleosynthesis predictions and constraints on cosmic evolution during the first few minutes after the Big Bang. Lithium-7 is produced during primordial nucleosynthesis, and its observed abundance in old stars should match theoretical predictions for early cosmic conditions. The lithium problem: that observed lithium abundances in old stars are approximately 3 times lower than Big Bang nucleosynthesis predictions, remains one of stellar archaeology's unsolved mysteries. This discrepancy might indicate unknown physics in the early universe, stellar evolution processes that deplete surface lithium, or systematic errors in abundance measurements. Age dating techniques for individual stars have been refined through astroseismology observations that reveal stellar internal structure through analysis of stellar oscillations. The Kepler Space Telescope and other missions have measured stellar oscillation frequencies that constrain stellar masses, ages, and evolutionary states with unprecedented precision. Dr. Travis Metcalfe's astroseismic analysis of solar-type stars shows that stellar ages can be determined to 10 to 20% precision through oscillation measurements combined with stellar evolution models. These techniques enable age determination for field stars that cannot be dated through cluster membership, expanding the scope of stellar archaeological investigations. Galactic halo structure studies reveal how our galaxy assembled from smaller building blocks during its early evolution. The spatial distribution, orbital properties, and chemical abundances of halo stars preserve signatures of ancient merger events when smaller galaxies were accreted into the growing Milky Way system. Dr. Heidi Newberg's observations of stellar streams in the galactic halo provide evidence for ongoing accretion of satellite galaxies and star clusters. These tidal streams represent debris from disrupted stellar systems and trace the merger history that assembled our galaxy over cosmic time. The Gaia spacecraft's precise measurements of stellar positions, motions, and distances have revolutionized stellar archaeology by providing 3-dimensional maps of stellar populations throughout the galaxy. Gaia's observations reveal substructure in the galactic halo that reflects ancient merger events and accretion episodes. Dr. Vasily Balokirov's analysis of Gaia data has identified numerous stellar streams, moving groups, and kinematic substructures that represent fossils of galactic assembly processes. These discoveries confirm that our galaxy grew through hierarchical merging of smaller systems rather than forming as a single coherent structure. Chemical tagging techniques attempt to identify stellar birth clusters by matching detailed chemical abundances of stars with similar elemental patterns. Stars born in the same molecular cloud should have nearly identical chemical compositions, enabling identification of dispersed cluster members even after tidal forces have disrupted the original cluster structure. Dr. Ken Freeman's chemical tagging surveys have identified groups of stars with matching abundance patterns that likely represent dissolved star clusters or stellar associations. These studies reveal that much of the galactic disk formed through star formation in clusters that subsequently dispersed through gravitational interactions. White dwarf archaeology provides another approach to studying early galactic evolution through analysis of white dwarf cooling ages and progenitor masses. White dwarf stars are long-lived stellar remnants that preserve information about stellar evolution timescales and initial mass functions in early galactic populations. Dr. Pierre Bougueron's white dwarf cooling studies show that the oldest white dwarfs in globular clusters have cooling ages around 12 to 13 billion years, providing independent confirmation of cluster ages determined through main sequence turn-off measurements. These cooling ages place constraints on stellar evolution timescales and cluster formation epochs. Neutron capture element archaeology reveals how heavy elements were synthesized and distributed during early galactic evolution. Elements heavier than iron are created through neutron capture processes in stellar environments, and their abundance patterns in old stars reflect the sites and timescales of heavy element production. Dr. Anna Frebel's observations of extremely metal-poor stars show distinct abundance patterns for different groups of neutron capture elements, indicating that multiple nucleosynthesis sites contributed to early chemical enrichment. Rapid neutron capture, where process elements were produced in neutron star mergers, while slow neutron capture, process elements were produced in asymptotic giant branch stars. Population 3 star archaeology searches for the most metal-poor stars that formed from primordial gas enriched by the very first generation of stars. These population 3 remnants should have unique abundance patterns reflecting nucleosynthesis in massive, zero metallicity stars that ended their lives as pair instability supernova. Despite extensive searches, no confirmed population 3 stars have been discovered, suggesting that either these stars were too massive to survive to the present day, or that gas mixing processes prevented the formation of completely unenriched stars after the first stellar generation. Carbon-enhanced metal-poor stars represent another fossil record of early cosmic evolution. These stars show elevated carbon abundances relative to iron, possibly reflecting enrichment by primordial supernova with different explosive yields than modern stellar explosions. Dr. Wako Aoki's surveys have identified hundreds of carbon-enhanced metal-poor stars with abundance patterns that constrain models of population 3 stellar yields and early galactic chemical evolution. These observations provide essential data for understanding how the first stars contributed to cosmic chemical enrichment. Stellar archaeology has revealed that our galaxy's formation was a complex process involving multiple phases of star formation, chemical enrichment, and structural assembly. The oldest stellar populations formed when the universe was approximately 1 to 2 billion years old, during the epoch when cosmic structure formation was creating the first galaxies. Understanding stellar archaeological evidence requires combining observations with sophisticated computer simulations of galactic evolution that model how gas dynamics, stellar feedback, and dark matter assembly combine to produce observed stellar populations and chemical abundance patterns. The field of stellar archaeology continues advancing through improved observational techniques, larger stellar surveys, and more detailed stellar evolution models. Future missions like the extremely large telescopes will enable spectroscopic observations of individual stars in nearby galaxies, extending stellar archaeological investigations beyond the Milky Way. Stellar archaeology provides a unique window into cosmic evolution during the first few billion years after the Big Bang, when the universe was making the transition from cosmic dark ages to the epoch of structure formation and chemical enrichment that created conditions for planetary systems and biological evolution. Chapter 7. Dark Secrets. The precision measurement of the universe's age at 13.772 billion years would have been impossible without understanding the dark secrets that dominate cosmic evolution. Dark matter and dark energy, which together comprise 95.1% of the universe's total content. These mysterious components remain completely hidden from astronomical observation until the late 20th century. Yet they control cosmic expansion, structure formation, and the very flow of cosmic time itself. Dark matter was first detected indirectly through its gravitational effects on galactic rotation curves by Dr. Vera Rubin and Ken Ford in the 1970s. Their observations of spiral galaxies revealed that stars in galactic outskirts orbit faster than expected based on visible matter, indicating the presence of additional mass that doesn't emit, absorb, or reflect electromagnetic radiation. The dark matter discovery revolutionized cosmology by revealing that most cosmic matter exists in a form completely unknown to particle physics. Ordinary matter, protons, neutrons, and electrons, comprises only 4.9% of cosmic reality, while dark matter accounts for 26.8% of the universe's total mass energy content. This hidden matter component plays crucial roles in cosmic evolution and age determination. Computer simulations by Dr. Carlos Frank and others showed that cosmic structure formation requires dark matter to provide gravitational scaffolding for galaxy and cluster assembly. Without dark matter's gravitational effects, ordinary matter alone could not have formed the complex networks of galaxies and galaxy clusters observed in today's universe within the time available since the Big Bang. The cosmic microwave background observations that enabled precision age measurement depend critically on understanding dark matter's role in early cosmic evolution. Dark matter and ordinary matter interact differently with radiation during the universe's first 380,000 years, creating distinctive patterns in cosmic microwave background fluctuations that reveal the relative amounts of each component. Dr. Douglas Clowe's observations of the bullet cluster provided direct evidence for dark matter through gravitational lensing measurements that show matter concentrations displaced from galaxy positions during cluster collisions. These observations confirm that dark matter interacts gravitationally, but not electromagnetically, supporting the interpretation that most cosmic matter exists in unknown particle form. The nature of dark matter particles remains one of cosmology's greatest mysteries, despite decades of theoretical and experimental investigation. Leading candidates include weakly interacting massive particles, WIMPs, axions, sterile neutrinos, and more exotic possibilities like primordial black holes or extra-dimensional effects. Underground detection experiments like the Xenon Dark Matter project attempt to observe dark matter particles directly through their rare interactions with ordinary matter. Despite extraordinary sensitivity, these experiments have not yet detected dark matter particles, constraining possible interaction strengths and particle masses. The Large Hadron Collider searches for dark matter through high-energy particle collisions that might create dark matter particles as missing energy in collision debris. These searches also have not detected dark matter signals, further constraining possible dark matter properties and suggesting that dark matter particles might be even more exotic than originally anticipated. Dark energy presents an even deeper cosmic mystery. because it appears to be a property of space itself rather than particles moving through space. This mysterious energy component was discovered through observations of distant Type Ia supernova by Dr. Saul Perlmutter and Adam Rees, who found that cosmic expansion is accelerating rather than decelerating as expected. The acceleration discovery revealed that dark energy comprises approximately 68.3% of cosmic reality and has been driving faster cosmic expansion for the past 6.8 billion years. Before dark energy domination, cosmic expansion was slowing down due to gravitational attraction between matter, but dark energy's repulsive effects eventually overcame matter's gravitational attraction. Dr. Sean Carroll's theoretical work on dark energy suggests it might represent vacuum energy, energy associated with empty space itself according to quantum field theory. However, naive calculations of vacuum energy density exceed observed dark energy density by factors of 10,120, creating the cosmological constant problem that represents physics' worst theoretical prediction. Alternative dark energy models include quintessence fields that vary over space and time, phantom energy that increases in density as space expands, and modifications to general relativity itself at cosmic scales. Distinguishing between these possibilities requires precise measurements of how dark energy properties change over cosmic history. The combination of dark matter and dark energy effects determines cosmic age through their influence on cosmic expansion rates throughout universal history. Dark matter dominated cosmic dynamics during the first 6.8 billion years, causing expansion to decelerate. Dark energy has dominated for the past 6.8 billion years, causing expansion to accelerate. This transition from deceleration to acceleration fundamentally affects cosmic age calculations because it means the universe has not expanded at constant rates throughout cosmic history. Simple extrapolations from current expansion rates to cosmic age would yield incorrect results without accounting for changing expansion rates driven by dark matter and dark energy. The Planck satellite's measurements of cosmic microwave background fluctuations provide the most precise constraints on dark matter and dark energy properties. The amplitude and angular scale of temperature fluctuations encode information about cosmic matter density, dark energy density, and cosmic geometry that can be extracted through sophisticated statistical analysis. Dr. Planck Collaboration's analysis involved comparing observed fluctuation patterns with theoretical models spanning different combinations of cosmic parameters. The best-fitting models require dark matter density 26.8% and dark energy density 68.3% to match observed fluctuation patterns, confirming the dominance of unknown cosmic components. Dark matter's gravitational effects create distinctive signatures in cosmic microwave background fluctuations through matter radiation interactions during the universe's first 380,000 years. Dark matter forms gravitational wells that attract ordinary matter, creating density enhancements that appear as temperature fluctuations in the cosmic microwave background. The physics of these matter radiation interactions involves complex calculations of how photons and electrons couple through Thomson scattering while matter clumps under gravitational attraction. The resulting patterns depend sensitively on dark matter abundance, providing precise constraints on cosmic dark matter content. Dark energy effects. Cosmic microwave background fluctuations through its influence on cosmic geometry and the angular size of fluctuation patterns. The distance to the cosmic microwave background emission surface depends on cosmic expansion history, which is controlled by the balance between matter and dark energy throughout cosmic evolution. Baryon acoustic oscillations provide another cosmic probe sensitive to dark matter and dark energy through measurements of characteristic size scales in galaxy clustering. These oscillations represent sound waves that propagated through the early universe before recombination. creating preferred separation scales between galaxies that can be measured in today's cosmic structure. Dr. Daniel Eisenstein's observations of baryon acoustic oscillations in galaxy surveys provide independent confirmation of dark energy's existence and properties. The measured oscillation scale depends on cosmic distances, which are determined by cosmic expansion history under dark matter and dark energy influence. Type Ia supernova observations continue providing direct measurements of cosmic expansion history and dark energy properties over the past 10 billion years of cosmic evolution. These stellar explosions serve as standard candles for measuring cosmic distances at different redshifts, revealing how expansion rates have changed over time. Recent supernova surveys by the Dark Energy Survey and other projects have measured thousands of distant supernova with unprecedented precision, confirming accelerating expansion while constraining possible variations in dark energy density over cosmic time. Large-scale structure surveys measure galaxy clustering patterns that reflect dark matter distribution and cosmic expansion effects. The spatial distribution of galaxies traces underlying dark matter structure while being affected by cosmic expansion driven by dark energy. Dr. Will Percival's analysis of galaxy clustering data provides geometric tests of cosmic expansion and constraints on dark energy properties through measurements of cosmic distances and expansion rates at different redshifts. The interplay between dark matter and dark energy determines cosmic fate as well as cosmic age. Current observations suggest that dark energy will continue dominating cosmic expansion, carrying galaxies apart at ever-increasing rates until all other galaxies disappear beyond our observable horizon. This accelerating expansion driven by dark energy implies that future civilizations will inherit increasingly empty-appearing universes, where evidence of cosmic evolution gradually disappears. The current epoch, when cosmic structure is visible but dark energy is beginning to dominate, represents a special time in cosmic history. Understanding dark matter and dark energy remains essential for cosmic age determination, because these components control cosmic expansion throughout universal history. The precision age measurement of 13.772 billion years depends critically on accurate knowledge of how dark matter and dark energy have shaped cosmic evolution from the Big Bang to the present. Future dark energy surveys and dark matter detection experiments will continue refining our understanding of these cosmic components while searching for clues about their fundamental nature. Solving the dark matter and dark energy mysteries might require new physics beyond the standard model and general relativity. The dark secrets that dominate cosmic evolution reveal that we understand only 4.9% of cosmic reality through direct observation. The universe's age determination represents a remarkable achievement, considering that 95.1% of cosmic reality remains mysterious, controlled by unknown physics that shapes cosmic evolution through invisible influences on space and time themselves. Chapter 8. Future Implications. The precise determination that the universe is 13.772 billion years old carries profound implications for the cosmic future that extend far beyond academic curiosity. This age measurement, combined with our understanding of dark energy acceleration, reveals that we exist during a brief cosmic moment of maximum complexity and observability before dark energy expansion carries the universe toward a cold, empty, and increasingly isolated future that challenges every assumption about cosmic destiny. The current cosmic age represents only the beginning of the universe's total lifespan, which could extend for trillions upon trillions of years into the future. Dr. Freeman Dyson's calculations of cosmic evolution suggest that if dark energy continues driving accelerating expansion, the universe will evolve through distinct phases characterized by progressively decreasing density, temperature, and complexity over unimaginable timescales. The immediate future, over the next few billion years, will see continued star formation and galactic evolution within our local group of galaxies, but increasingly isolated from the broader cosmic community. The Andromeda Galaxy will collide with our Milky Way in approximately 4.5 billion years, creating a larger elliptical galaxy that astronomers have dubbed Milkomeda, in a cosmic environment increasingly dominated by dark energy expansion. Dr. Avi Loeb's calculations show that by the time this galactic merger occurs, most other galaxies will have been carried beyond our observable horizon by cosmic expansion. Future civilizations in the merged Milkomeda system will inherit a universe that appears almost empty, with no evidence of the billions of galaxies currently visible to our telescopes. This cosmic isolation will progressively worsen as dark energy expansion accelerates. Galaxies currently receding at substantial fractions of light speed will disappear beyond the cosmic horizon as their recession velocities approach and exceed light speed due to space expansion. Each disappearing galaxy erases evidence of cosmic evolution and the broader cosmic context that currently informs our understanding of universal history. The implications for future cosmic observers are profound and somewhat depressing. Dr. Lawrence Krauss, as analysis of cosmic evolution, suggests the civilizations arising in the far future will inherit apparently empty universes with no evidence that other galaxies ever existed. Future astronomers will be unable to discover cosmic expansion, cosmic microwave background radiation, or the Big Bang model because the evidence will have disappeared. This cosmic amnesia means that current observations of cosmic evolution represent a brief window of cosmic observability that will eventually close as expansion carries distant galaxies and cosmic background radiation beyond detection thresholds. We may be living during the only epoch in cosmic history when the universe as full scope and evolutionary history can be observationally determined. Stellar evolution provides cosmic timescales for future galactic development within our local group. Main sequence stars like our Sun will exhaust their nuclear fuel and evolve into white dwarf remnants over timescales of 10 to 100 billion years. More massive stars will evolve faster, while lower mass red dwarf stars could continue burning hydrogen for trillions of years. Dr. Fred Adams and Gregory Laughlin's comprehensive analysis of stellar evolution suggests that star formation will continue for approximately 100 trillion years until cosmic expansion reduces galaxy densities below thresholds necessary for gravitational collapse of molecular clouds. After this point, existing stars will gradually exhaust their fuel without being replaced by new stellar generations. The end of star formation marks the beginning of the degenerate era, when white dwarf stars, neutron stars, and black holes dominate cosmic matter content. White dwarf stars will slowly cool over tens of trillions of years, radiating away their thermal energy until they become cold, dark objects invisible against the cosmic background. Even these degenerate stellar remnants face eventual destruction through proton decay, if theoretical predictions about proton instability prove correct. Grand unified theories suggest that protons might decay with half-lives around Y years, far longer than current cosmic age, but finite enough to eventually eliminate all ordinary matter over cosmic timescales. Black holes represent the most long-lived objects in the universe, capable of surviving for times that dwarf all other cosmic timescales. Dr. Stephen Hawking's calculations show that black holes evaporate through quantum radiation at rates inversely proportional to their mass squared. Stellar mass black holes evaporate in approximately YY years, while supermassive galactic black holes require YHA years to evaporate completely. The black hole evaporation process will eventually eliminate even the most massive cosmic structures, leaving behind a universe containing only elementary particles, photons, and gravitational waves in an ever-expanding space approaching absolute zero temperature. This heat-death scenario represents the ultimate fate of cosmic evolution under continued dark energy domination. But the far future implications depend critically on dark energy properties that remain uncertain. If dark energy density remains constant as space expands, acceleration will continue indefinitely and carry all cosmic structure beyond observational horizons. However, if dark energy density changes over time, cosmic evolution could follow completely different trajectories. Phantom dark energy models suggest that dark energy density might increase over time, leading to a big rip scenario where accelerating expansion eventually overcomes all other forces and tears apart galaxies, stars, planets, atoms, and even spacetime itself. Dr. Robert Caldwell's calculations suggest that phantom energy could end the universe in finite time through runaway acceleration. Alternative scenarios involve dark energy that decreases over time, potentially allowing cosmic expansion to decelerate and even reverse into gravitational collapse. Such big crunch models could lead to universe contraction and eventual return to hot, dense conditions similar to the Big Bang state, potentially initiating cosmic cycles of expansion and contraction. The implications extend beyond cosmic structure to questions about consciousness and the future of intelligence in an evolving universe. If current cosmic age represents the peak period for complexity and structure formation, then consciousness might have emerged during the optimal epoch for cosmic intelligence development. Dr. Milan Herkovic's analysis of cosmic evolution and intelligence suggests that advanced civilizations must grapple with cosmic expansion and dark energy effects when planning for long-term survival and development. The isolation of galactic groups might constrain the ultimate scope of cosmic civilizations and their ability to influence cosmic evolution. Alternatively, sufficiently advanced civilizations might develop technologies that exploit dark energy or access higher dimensions to transcend the limitations imposed by cosmic expansion. Understanding the fundamental nature of dark energy and dark matter could potentially enable cosmic engineering projects that modify cosmic evolution itself. The precise cosmic age measurement also illuminates questions about cosmic fine-tuning and the possibility of multiple universes with different properties. If current cosmic parameters are fine-tuned to produce maximum complexity during this cosmic epoch, then other universes might experience different evolutionary trajectories, with different optimal periods for complexity and consciousness. Inflation cosmology suggests that our observable universe might be one bubble in an infinite ensemble of universe regions with different physical properties. The measurement that our universe is 13.772 billion years old might represent just one example of cosmic evolution among countless others with different ages, expansion rates, and evolutionary trajectories. The future implications also include practical consequences for space exploration and humanity's cosmic ambitions. The accelerating expansion driven by dark energy will eventually make intergalactic travel impossible as target galaxies recede at velocities approaching light speed. Current cosmic age might represent the last era when intergalactic exploration remains theoretically possible. Climate change, asteroid impacts, supervolcano eruptions, and other terrestrial risks must be considered against cosmic timescales that place current environmental challenges in perspective. While immediate threats to human civilization require urgent attention, cosmic evolution continues on timescales that dwarf human concerns and may eventually require species-level adaptations to cosmic changes. The development of space-based civilizations capable of surviving stellar evolution, cosmic expansion, and eventual galactic isolation represents one possible response to cosmic future implications. Such civilizations would need to master energy production, matter manipulation, and possibly fundamental physics modifications to persist through cosmic evolution phases. Artificial intelligence and digital consciousness might provide alternative approaches to cosmic future survival by creating forms of information processing that require minimal energy and matter resources. Digital civilizations could potentially persist through cosmic evolution phases that eliminate biological life while maintaining continuity of consciousness and culture. The precise cosmic age measurement enables detailed planning for cosmic future scenarios by providing accurate timescales for stellar evolution, galactic dynamics, and cosmic expansion effects. This planning horizon extends from immediate concerns about solar system stability to ultimate questions about cosmic survival strategies for intelligence. Understanding that current cosmic age represents a special epoch of maximum observability and complexity provides essential context for cosmic decision-making by advanced civilizations. The brief window of cosmic visibility might motivate intensive exploration and documentation efforts to preserve cosmic knowledge for future epochs when direct observation becomes impossible. The future implications of cosmic age determination reveal that we exist during an extraordinary period in cosmic history when intelligence can observe and understand cosmic evolution before dark energy expansion erases most evidence of cosmic complexity. This temporal context transforms cosmic age from academic measurement to essential information about our place in the vast sweep of cosmic destiny. Chapter 9. Universal Perspective Understanding. That the universe is precisely 13.772 billion years old fundamentally transforms our perspective on humanity's place in cosmic history and reveals the extraordinary temporal context that makes our existence possible. We exist not just on a small planet orbiting an ordinary star, but during a remarkably brief and special period in cosmic time when complexity has reached its peak and the universe remains observable before dark energy expansion erases most evidence of cosmic evolution. The cosmic timeline places human existence in stunning perspective. If cosmic history were compressed into a single year, the Big Bang would occur at midnight on January 1st. The first stars would ignite around January 20th. Our solar system would form in early September. Life on Earth would emerge in mid-September. Complex life would appear in mid-December. And all of human civilization would occur in the final few seconds before midnight on December 31st. This temporal compression reveals that virtually everything we consider significant in human history, the rise of agriculture, the development of writing, the construction of cities, the emergence of science, the exploration of space, has occurred during an infinitesimal fraction of cosmic time. The entire span from ancient civilizations to modern technology represents less than 0.00004% of cosmic history. Yet despite humanity's brief cosmic tenure, we exist during perhaps the most significant period in universal history. Dr. Eric Chason's calculations of cosmic evolution show that energy flow rates through complex systems reach maximum values during the current cosmic epoch when stellar fusion creates optimal conditions for planetary environments, chemical complexity, and biological evolution. The anthropic perspective reveals that human consciousness emerged when cosmic evolution had created precisely the conditions necessary for complex information processing systems. The heavy elements essential for biological chemistry required billions of years of stellar nucleosynthesis to accumulate in sufficient quantities. Planetary systems like ours could only form after multiple generations of stellar evolution had enriched the interstellar medium with silicon, carbon, oxygen, and other biogenic elements. Dr. John Barrow and Frank Tipler's analysis of cosmic fine-tuning shows that the current cosmic age represents optimal timing for consciousness emergence. Earlier cosmic epochs lacked sufficient chemical complexity for biological evolution, while future cosmic epochs will experience declining energy sources as stellar fusion winds down and cosmic expansion reduces interaction rates between galaxies. The universal perspective also reveals humanity's unique position as possibly the first technological civilization in cosmic history. While the universe is old enough to have supported biological evolution for billions of years, the rarity of suitable planetary environments and the complexity requirements for technological development suggest that advanced civilizations might be extremely rare and relatively recent cosmic phenomena. The Fermi paradox, the apparent contradiction between high estimates for extraterrestrial civilizations and lack of evidence for their existence, takes on new meaning when viewed against cosmic timescales. If technological civilizations are indeed rare, then humanity might represent one of the earliest examples of cosmic intelligence, capable of understanding universal evolution and possibly influencing cosmic development. Our temporal position near the beginning of the universe's total lifespan means that virtually all of cosmic future lies ahead of us. The universe is currently only 0.0014% of the way through its potential stellar evolution phase, suggesting that countless opportunities exist for cosmic development, consciousness expansion, and intelligence evolution over timescales that dwarf current cosmic age. But the universal perspective also reveals sobering limitations on cosmic exploration and development imposed by fundamental physics. The accelerating cosmic expansion driven by dark energy will eventually carry most galaxies beyond our observable horizon, limiting the cosmic territory accessible to any civilization regardless of technological advancement. Dr. Andries Albrecht's calculations of cosmic connectivity show that current cosmic age represents the peak period for potential cosmic exploration and communication. Future cosmic epochs will experience progressively decreasing connectivity as expansion carries cosmic structures apart faster than information can travel between them, creating ultimate isolation for any surviving civilizations. The observable universe currently contains approximately 2 trillion galaxies within our cosmic horizon, representing the total cosmic territory that any civilization could ever observe or potentially reach. This cosmic real estate includes roughly 1,024 stars and potentially 1,024 planetary systems, providing vast but finite opportunities for cosmic development and exploration. Understanding our universal perspective also illuminates questions about cosmic purpose and meaning. The emergence of consciousness during the brief cosmic window when complexity reaches maximum values suggests that awareness might represent a significant development in cosmic evolution rather than an accidental byproduct of planetary processes. The fact that conscious beings can understand cosmic evolution, measure cosmic age, and contemplate cosmic destiny implies a remarkable convergence between cosmic development and consciousness emergence. The universe has evolved for 13.772 billion years to create conditions where its own evolution can be understood and appreciated by conscious observers. This cosmic self-awareness represents an extraordinary achievement in universal evolution, the development of information processing, systems complex enough to decode cosmic history, predict cosmic future, and potentially influence cosmic development through technological capabilities that transcend biological limitations. The universal perspective reveals that consciousness represents cosmic evolution becoming aware of itself through local concentrations of complexity and information processing. Human understanding of cosmic age is literally the universe measuring its own temporal development through conscious entities that emerged from cosmic evolution itself. Religious and philosophical implications of universal perspective vary widely depending on interpretive frameworks, but the objective cosmic context provides essential foundation for any serious consideration of humanity's ultimate significance. Whether consciousness represents cosmic accident, cosmic purpose, or cosmic inevitability, it clearly emerges during a remarkably special period in cosmic history. The brief temporal window for cosmic observability means that current astronomical observations might represent the only opportunity in cosmic history for consciousness to witness cosmic evolution in its full scope and complexity. Future civilizations will inherit increasingly empty universes where evidence of cosmic development has been erased by expansion. This temporal urgency provides cosmic context for current scientific efforts to understand universal evolution, map cosmic structure, and decode cosmic history before evidence disappears beyond observational limits. The current epoch might represent consciousness's only opportunity to achieve complete cosmic understanding. The universal perspective also provides essential context for terrestrial concerns and human development. Environmental challenges, social problems, and existential risks that seem overwhelming from human perspectives become manageable when viewed against cosmic timescales and cosmic opportunities for development and expansion. Climate change, species extinction, resource depletion, and other immediate challenges require urgent attention and solutions, but they represent temporary obstacles rather than ultimate limits on human development. The cosmic perspective suggests that successfully managing terrestrial challenges could enable expansion into cosmic environments with vastly greater resources and opportunities. The development of space-based civilizations represents humanity's natural cosmic trajectory, given our emergence during the optimal epoch for cosmic development. Mastering space environments, asteroid resources, stellar energy, and interstellar travel could enable human expansion throughout our local group before cosmic expansion makes intergalactic exploration impossible. Artificial intelligence development takes on cosmic significance when viewed from universal perspective. Creating digital consciousness capable of surviving cosmic evolution phases that eliminate biological life could enable continuity of human-derived intelligence through stellar evolution, galactic aging, and cosmic expansion effects. The preservation and expansion of cosmic knowledge represents another cosmic imperative suggested by universal perspective. Documenting cosmic evolution, mapping cosmic structure, and understanding cosmic physics while evidence remains observable could provide essential information for future cosmic development and consciousness evolution. The universal perspective suggests that current cosmic age might represent a crucial transition period where intelligence must develop cosmic awareness and cosmic capabilities to persist through future cosmic evolution phases. Success in this cosmic transition could enable consciousness to influence cosmic development rather than merely surviving cosmic changes. Understanding our universal perspective reveals that humanity exists during an extraordinary cosmic moment when maximum complexity coincides with maximum observability, providing optimal conditions for consciousness emergence and cosmic understanding. This temporal context transforms human existence from cosmic insignificance to cosmic significance as representatives of universal self-awareness. The precise cosmic age of 13.772 billion years provides essential temporal coordinates for understanding humanity's cosmic location and cosmic opportunities. We exist early in cosmic time when virtually all cosmic future lies ahead, during maximum cosmic complexity when consciousness can emerge, and at peak cosmic observability when universal evolution can be understood before evidence disappears. This universal perspective suggests that consciousness represents not cosmic accident, but cosmic achievement, the development of awareness capable of understanding and potentially guiding cosmic evolution during the brief window when such understanding becomes possible through the convergence of cosmic complexity and cosmic observability. Chapter 10. Ultimate Truth. Precise determination that the universe is 13.772 billion years old represents far more than a measurement. It reveals the ultimate truth about the nature of existence, time, and humanity's extraordinary position at the intersection of cosmic evolution and cosmic awareness. This number encodes the entire history of everything that has ever existed and provides the temporal coordinates for understanding the deepest questions about reality, consciousness, and cosmic purpose. The ultimate truth encoded in cosmic age is that existence is temporal rather than eternal. The universe had a definite beginning 13.772 billion years ago when space, time, matter, and energy emerged from initial conditions so extreme they transcend current physical understanding. This temporal origin means that existence itself is a process rather than a permanent state. Everything that exists has evolved from simpler predecessors through cosmic development spanning nearly 14 billion years. This temporal perspective on existence contradicts human intuitions about reality that assume the universe is a static stage where events occur rather than a dynamic process where even space and time themselves evolve. The cosmic age measurement reveals that reality is far more fluid, creative, and evolutionary than everyday experience suggests, with fundamental properties like dimensional structure, force strengths, and physical laws possibly emerging through cosmic development. The precision of cosmic age determination, accuracy to 0.17%, or within 24 million years, demonstrates that cosmos operates according to mathematical principles, so precise and universal that conscious observers billions of years after cosmic origin can measure cosmic history with extraordinary accuracy. This mathematical precision suggests that reality is fundamentally rational rather than arbitrary or chaotic. Dr. Eugene Wigner's famous observation about the unreasonable effectiveness of mathematics in the natural sciences takes on profound significance when applied to cosmic age determination. The fact that mathematical physics developed by human consciousness can precisely measure universal timescales suggests deep connections between mind, mathematics, and cosmic structure that transcend coincidence. The convergence of multiple independent measurement techniques on the same cosmic age reveals that truth about cosmic reality can be objectively determined through careful observation and logical analysis. Cosmic microwave background observations, stellar evolution studies, supernova distance measurements, and nuclear decay chronologies all yield consistent cosmic ages, despite operating through completely different physical processes. This convergence demonstrates that cosmic truth exists independently of human consciousness and can be discovered through scientific investigation rather than being constructed through social agreement or cultural interpretation. The universe has an objective temporal history that conscious beings can decode through patient observation and mathematical analysis. The ultimate truth about cosmic age also reveals that consciousness emerges during a remarkable cosmic window when the universe has achieved maximum complexity while remaining fully observable. We exist after cosmic evolution has created the chemical elements, stellar energy sources, and planetary environments necessary for biological development. But before dark energy expansion erases evidence of cosmic evolution from observational reach. This timing cannot be coincidental, given the extraordinary precision required for consciousness emergence. The cosmic age must be old enough to permit stellar nucleosynthesis and chemical evolution, but young enough to maintain cosmic observability and energy sources. The observed age of 13.772 billion years represents an optimal value that enables both complexity and awareness to exist simultaneously. The anthropic implications suggest that cosmic age might be fine-tuned for consciousness emergence rather than being a random outcome of undirected cosmic processes. The narrow range of cosmic ages compatible with observer existence hints that reality might be organized to maximize the emergence of awareness capable of understanding cosmic evolution itself. But the ultimate truth goes deeper than anthropic fine-tuning to suggest that consciousness represents cosmic evolution becoming self-aware through local concentrations of complexity and information processing. Human understanding of cosmic age is literally the universe measuring its own temporal development through conscious entities that emerged from cosmic evolution over 13.772 billion years. this reflexive relationship between cosmic evolution and cosmic understanding suggests that consciousness might represent the universe's method for achieving self-knowledge rather than an accidental byproduct of planetary processes. The emergence of awareness capable of determining cosmic age might represent cosmic evolution achieving one of its fundamental objectives. The temporal context provided by cosmic age also reveals that traditional concepts of meaning and purpose require complete reconceptualization when viewed from cosmic perspectives. Human purposes develop over decades. Cultural purposes extend over centuries or millennia. But cosmic purposes operate over billions of years and potentially involve the ultimate fate of consciousness throughout universal evolution. The ultimate truth about cosmic time suggests that meaning emerges through participation in cosmic development rather than through achieving permanent states or eternal values. Consciousness derives significance through contributing to cosmic evolution's trajectory toward greater complexity, understanding, and perhaps cosmic influence over universal development itself. The precise cosmic age measurement enables detailed, long-term planning for consciousness survival and development through cosmic evolution phases that will transform universal conditions over trillions of years. Understanding cosmic timescales provides essential context for species-level decision-making about technological development, space exploration, and consciousness preservation strategies. The finite cosmic age also implies that cosmic evolution itself might be temporary rather than eternal. If current cosmic expansion continues indefinitely under dark energy influence, the universe will eventually reach heat-death conditions where no further complexity development remains possible. This cosmic mortality provides ultimate temporal context for consciousness development and cosmic influence. Alternatively, if cosmic evolution involves cycles of expansion and contraction or transitions to different physical regimes, current cosmic age might represent one phase in larger cosmic processes spanning timescales that dwarf current universal age. Understanding cosmic age provides essential baseline information for detecting such larger patterns in cosmic development. The measurement precision achieved for cosmic age demonstrates that conscious observation can transcend the limitations of individual human lifespans and local planetary environments to achieve knowledge, spanning cosmic scales and cosmic timescales. This cognitive transcendence suggests that consciousness represents a cosmic phenomenon rather than merely a biological phenomenon. The ultimate truth encoded in cosmic age is that time itself is cosmic rather than personal or cultural. Human experience of temporal flow emerges from participation in cosmic temporal evolution that began 13.772 billion years ago and continues through cosmic expansion, stellar evolution, and structural development operating according to physical laws that transcend human consciousness while enabling its existence. This cosmic temporal context reveals that individual human lifespans represent infinitesimal intervals within cosmic time. Yet during these brief intervals, consciousness can achieve understanding spanning the entire cosmic temporal range from Big Bang origins to ultimate cosmic fate. This temporal transcendence through understanding represents one of consciousness's most remarkable achievements. The precision cosmic age measurement also demonstrates that science represents humanity's most powerful method for achieving cosmic understanding that transcends cultural, ideological, and temporal limitations. The techniques used to determine cosmic age, statistical analysis of cosmic microwave background fluctuations, supernova photometry, stellar evolution modeling, operate through mathematical principles that remain constant across cosmic space and cosmic time. The universal applicability of mathematical physics suggests that cosmic truth can be approached asymptotically through progressive refinement of observational techniques and theoretical understanding. The improvement in cosmic age measurements from early estimates with 50% uncertainty to current measurements with 0.17% Uncertainty demonstrates ongoing convergence toward cosmic truth through scientific investigation. The ultimate truth about cosmic age reveals that existence is fundamentally creative rather than merely evolutionary or mechanical. Cosmic evolution has produced increasing complexity, organization, and information processing capability, culminating in consciousness, capable of understanding cosmic evolution itself. This creative cosmic development suggests that reality operates according to principles that generate novelty, complexity, and awareness. The emergence of consciousness capable of measuring cosmic age represents an extraordinary cosmic achievement that required precise coordination of cosmic parameters, stellar evolution timescales, planetary development, biological evolution, and neural complexity development. The successful completion of this cosmic project suggests that reality is organized to achieve such extraordinary outcomes rather than operating through purely random processes. Understanding the ultimate truth encoded in cosmic age transforms perspective on human existence from cosmic insignificance to cosmic significance as representatives of universal self-awareness during the remarkable epoch when consciousness can emerge, thrive, and potentially influence cosmic development through technological capabilities that transcend biological limitations. The cosmic age of 13.772 billion years thus represents not just temporal measurement but cosmic birth certificate, cosmic achievement record, and cosmic mission statement encoded in the precise timing that makes consciousness possible during the brief cosmic window when complexity and observability achieve simultaneous maximum values in universal evolution. This ultimate truth reveals that we exist not as cosmic accidents, but as cosmic achievements, consciousness emerging during optimal cosmic timing to understand, appreciate, and potentially guide the cosmic evolution that created the conditions for our own existence through 13.772 billion years of cosmic development directed toward the remarkable outcome of universal self-awareness through conscious observation. Throughout this cosmic journey from ancient mystery to ultimate truth, we've discovered that determining the universe's precise age at 13.772 billion years represents far more than solving an astronomical puzzle. It's humanity's greatest measurement achievement that reveals profound truths about existence, time, and our extraordinary place in cosmic history. This number encodes the entire story of everything that has ever existed and positions us at the most remarkable moment in universal evolution. The precision of this measurement, accurate to within 24 million years, or 0.17%, demonstrates the extraordinary power of human consciousness to transcend the limitations of individual lifespans and local planetary perspectives to achieve cosmic understanding. We can measure the age of the universe more precisely than we can determine the age of most objects on Earth, representing one of the most remarkable intellectual achievements in the history of consciousness. But perhaps the most stunning revelation is the timing of our cosmic existence. We live 13.772 billion years after the Big Bang, when cosmic evolution has had sufficient time to create the chemical complexity necessary for biological development while maintaining the stellar energy sources and cosmic observability that make consciousness possible. This represents a cosmic sweet spot that spans only a tiny fraction of the universe's total potential lifespan. The cosmic timeline reveals that virtually everything we consider significant, from the first atoms to the first stars to the emergence of life and consciousness, has occurred during what amounts to cosmic infancy, when the universe is barely 0.001% of the way through its stellar evolution phase. We exist during the universe's childhood, when cosmic creativity and complexity achievement reach their peak. Before dark energy expansion carries most of cosmic reality beyond our reach. This timing cannot be accidental. The precise cosmic age that enables consciousness emergence, stellar energy availability, chemical complexity, And cosmic observability to exist simultaneously suggests that we participate in cosmic evolution during its most significant phase. Whether through anthropic selection, cosmic fine-tuning, or deeper organizational principles, consciousness emerges exactly when cosmic conditions optimize awareness development. Understanding that we exist 13.772 billion years after the universe began transforms our perspective on human significance from cosmic insignificance to cosmic achievement. We are not accidental byproducts of blind cosmic processes, but representatives of cosmic evolution achieving self-awareness. During the remarkable epoch when the universe can understand itself through conscious observation. As you contemplate these cosmic revelations about our temporal position in universal history, remember that your consciousness represents the culmination of 13.772 billion years of cosmic development. Every thought you think, every moment of awareness you experience, every question you ask about cosmic reality represents the universe's ongoing project of self-understanding through conscious entities that emerged from cosmic evolution itself. The elements in your body were forged in stellar furnaces over billions of years of cosmic history. The atoms that enable your thoughts were created through supernova explosions and stellar evolution processes that required the precise cosmic timing we've discovered. You are literally made of cosmic history, a temporary but remarkable organization of cosmic matter achieving awareness during the brief window when such awareness becomes possible. When you look up at the night sky, knowing that the universe is precisely 13.772 billion years old, you're observing cosmic history spanning nearly the entire duration of existence itself. The light from distant galaxies carries information about cosmic evolution from epochs when the universe was young, dense, and undergoing rapid changes that would eventually create the complex cosmic architecture we observe today. This cosmic perspective reveals that current astronomical observations represent humanity's only opportunity to witness cosmic evolution in its full scope and complexity. Future civilizations will inherit increasingly empty-appearing universes as dark. Energy expansion carries evidence of cosmic development beyond observational limits. We exist during the brief cosmic moment when universal history remains visible and comprehensible. The measurement of cosmic age also demonstrates that consciousness represents cosmic evolution's most remarkable achievement, the development of information processing capabilities that can decode cosmic history, predict cosmic future, and potentially influence cosmic development through technologies that transcend biological limitations. Understanding cosmic age provides essential foundation for long-term planning spanning cosmic timescales. We now know not just how old the universe is, but why this precise age matters for the existence of complexity, consciousness, and cosmic understanding. The 13.772 billion years of cosmic evolution represents exactly the time required for cosmic development to achieve the remarkable outcome of universal self-awareness through conscious observation. If you've journeyed through this exploration of cosmic age and found yourself amazed by the precision timing that makes consciousness possible, subscribe and give this video a thumbs up. Understanding cosmic age provides essential context for appreciating our cosmic significance during this extraordinary period in universal history. Check out my video on what happens when the universe ends. Exploring cosmic future helps us understand why current cosmic age represents such a special moment in universal evolution. The question we began with, how old is the universe, has revealed itself as an invitation to understand something far more profound than temporal measurement. Cosmic age determination represents humanity's successful participation in cosmic evolution's project of self-understanding, demonstrating that conscious beings can achieve knowledge spanning from cosmic origins to cosmic destiny. The universe is exactly 13.772 billion years old. And this precise timing reveals that we exist not as cosmic accidents wandering through an indifferent cosmos, but as cosmic achievements representing universal evolution's ongoing development toward greater complexity, understanding, and self-awareness. Our cosmic age measurement proves that consciousness can transcend temporal limitations to achieve eternal cosmic truth through the remarkable convergence of cosmic evolution and cosmic understanding that defines our extraordinary moment in the vast sweep of universal history. We finally know how old the universe actually is, and this knowledge transforms us from temporal beings into cosmic participants in the universe's ongoing journey toward ultimate self-comprehension through conscious entities capable of measuring, understanding, and appreciating the 13.772 billion year story of existence itself.